Okay, welcome everybody. It is a pleasure for me to welcome you in this seminar of the GReTA series that is held every 2 weeks in this modality. The speaker of today is Alexandre Fernandez, who will report about his work in his PhD thesis about specialized synchronous computation with global transformations. So I'm very interested to listen to this topic, which probably also has relations with the work done in the community of graph transformation about semantics of concurrent computations using graph transformation. So, Alexandre, I leave the stop to you, please.
Thank you, Andrea, for your neat introduction. And first, I would like to thank the organizers for letting me have this talk. So, as you said, my talk is about global transformations, which is a new framework that I work on in my PhD to describe spatialized synchronous computation over different kind of spaces. So, so the idea of this formalism. The idea of this formalism comes from the observation that there is some specific class of dynamical system that works in the same way. So, for instance, there is cellular automata that act over regular grids by applying some local function in a synchronous fashion. And there is other systems similar systems such as Lindenmayer system that acts over worlds, or extensions of this system over graphs like causal graph dynamics. And so the common point between this system is that they are all described through local rules, and the rules are meant to be applied everywhere in the input object in a synchronous fashion. And an important part is that the process of selecting which rule are applied or not is entirely deterministic. So before this work, there was no general approach to this or framework for describing this system when the space is dynamic. There was either asynchronous or maximal parallel approaches. So, for example, I see graph grammars as an asynchronous approach, or a system over specific spaces, such as causal graph dynamics that permits a lot of different dynamics, but only over some class of graphs. So, but in fact, we observe that these different systems work on different structures, but in the same ways. So they are all described by these local rules, and the application over some input object can be summarized as follows. So first, we decompose the input by finding every possible place we can apply a rule in it. Then we apply the local rules, and then we can recompose all the local results to get the output. So this formalism were introduced in the first time in 2015 by my PhD supervisor, Lyon and Antoine Spicher, to tackle the local specification of some simple process called triangular mesh refinement. So this process is simple. You take some 3D mesh in input, and you want to subdivide its triangle to get a final mesh. And whereas it is simple and seem local, there was no rule-based specification of it before this. Because if one tried to design such kind of specification, it will come up with this kind of rule, sending a triangle to a subdivided triangle. So here I represent triangle by graphs. So the problem with this specification, it is that it is indeed simple, but it is not complete. It doesn't explain what happens on the overlaps between two triangles. So for instance, if we take this graph in input, what you should want is that so you have two triangles sharing some common edge, and what you would want is that this the result should have the two subdivided triangles still glued together. But this kind of graph is completely compliant with the rules because the rule doesn't say what to do in this situation. So The intuition behind global transformation comes from trying to complete this specification. So now I will try to apply my little step of computation. So first, I decompose the object by finding every possible occurrence of a triangle in it. So I find two triangles in the input, which by the rules give me that there should be two subdivided triangles in the output. And here we have a problem. We want to express that these two triangles should be glued together. And to express this, we must observe that it comes from the fact that these two triangles share some common edge in the input. So let's add a rule sending triangles to edges to subdivided edges. And now we have three unrelated local results, and we need to relate them somehow. So we will add inclusions between the left-hand side of the rules here. We'll observe that the edge was included in the two triangles. And now we make our rules not only to send graphs to graphs, but also graphs inclusions to graph inclusions. Okay, and now we have enough information to recover the result that we wanted. So my goal in this last year were to develop this formalism, because at the start it was only restricted to this example of graphs. And while doing this, I wanted to support the claim of generality of the approach by describing already known systems such as cellular automata, and also studying new ones such as global graph transformations or global non-deterministic computations. So, and the general question that interests me on these systems is how do we guarantee some global feature of the computation only by the mean of the local rules? Okay, so in this talk, I will first define global transformations and give example of words. Then I will briefly introduce global graph transformations. Then I will focus on the sequentialization of global transformation. Then I will introduce categorical tools that permit to relate the local level and the global setting. And finally, I will speak a bit how to represent non-determinism in this setting. So let's start with the definition of a global transformations. And as example, let's take the simplest of such systems, which are Lindenmayer systems. So these systems are simply mapping from words to words over some alphabets, specified locally by a function from letters to words. So the global function just apply the local function on each letter of the input word and takes the concatenation of the obtained local results. So for instance, if we send A to B and B to AB, and we apply this on the word ABB, we should get BAB. Okay. So now I need some way to, so I want to formalize this system, but I want to be able to do a lot of other kind of system over different kind of data. So I want a way to abstract my data, my notion of space away. So here I'm considering words, but as we have seen in the introduction, we want to consider also graphs or other things. And the important thing I want to talk about is comes from, as we have seen in the introduction, in the last slides, we want to consider occurrences of an object on another. So we want to describe somehow how something is a part of another. So we can think of an order structure, but in fact, I need to differentiate between different occurrences of word in another. So here, for example, for A, I want to consider the two possible inclusion of A in the word AA. So here at the first letter or at the second letter. So I will work in a category W, having for object words, and for morphisms, integral representing on which position you find a word in another. Then I want my computation to respect this structure. So it will be a functor. So here, for example, I have a functor sending A to B, B to AB, and AB to BAB, and we can see that it should represent the computation of the Lindenmayer system that we have seen in the example. So then global transformation is simply such functor that can be presented by a category of by a set of local rules. So in fact, a category of local rules, because we have seen that we want to consider mappings from object to object, but also we have rules inclusions. So let's take some category of local rules with two functor L and R from this category to the category of words. So for example, I have a rule that sends A to B, a rule that sends B to AB. And as we have seen in the introduction, we want to consider also the every possible overlaps between the letters. So here I need to add a rule for the empty word, sending the empty word to itself. Then I will also consider every possible inclusion of the empty word at the beginning and the end of each letter and map them to inclusions of the empty word at the beginning and the end of each resulting word. So the inclusions in the right-hand side, we will use for decomposing the input, and the inclusion in the right-hand side will be used to recompose the output. So then we can formalize our three steps of application that we have seen before as follows. So we take some input objects, so here the word BBA, and we compute the comma category L over BBA of any possible occurrences of a left-hand side of a rule inside the object, and where morphism are left-hand side of rule inclusion, making these occurrences commute. So this gives this red zigzag diagram here expressing that in the input there is B then A, and then we apply the local rules to get this blue zigzag diagram expressing that in the output, there should be AB then B. And then we can recompose, we will recompose all this local result together by taking the colimit of this diagram. So as you see, this formalism only uses the categorical language and is not really dependent of the internal structure of the category of interest, so here the category of words. The only thing that we need is that this colimit construction to be defined for the diagram that we have to consider. So this formalism can be used to do rewriting on category representing not words, but graphs or trees, etc. But here to express that I am able to represent Lindenmayer system, I must guarantee that if we take the colimit of this kind of blue zigzag diagram, we should get the concatenation of all the local results. So here I will just recall a bit what is a colimit, but I will be a bit fast because I think a lot of people know this here. So a colimit, you take a you take the colimit of some diagram, which is a collection of objects and arrows of some category. And first we define what is a cocoon. So a cocoon is some object of the category together with component morphism from each object of the diagram that is compatible with the morphism of the diagram. And then the colimit, if it exists, is just the best candidate cocoon in the sense of it factor uniquely through each other cocoon. So there is a unique morphism from the green cocoon to any other yellow cocoon. And so now what we need to do is just to check that this construction in fact compute the concatenation in the category of words, which can be shown easily. So you take a diagram where you have U and V and the empty word included at the end of U and the beginning of V. Then you can check easily that if you take this cocoon having U, the concatenation of U and V in the apex, you get that this is the colimit of this diagram. And so this permits to represent, to do the full step, the computation of any Lindenmayer system. And in fact, we can also represent a bigger class of Lindenmayer system that are context sensitive. So this is all for words for the moment. So now let's try to rewrite graphs a bit. So what we will do is in place of the category of words, we take the category of graphs. So here I mean the category of quivers, which are directed multi-graphs. And one important thing is that for the decomposition process, I want to restrict to injective morphisms because I want, for example, my rule for triangles, I want it to apply only to real triangle, to proper triangle in my input and not to degenerate cases where you glue some edges together or morphism or nodes together. So let's try to define a rule system in this category GI, which is the subcategory of the subcategory of graphs, having all graphs and only injective graph morphisms. So we have a rule sending triangles to subdivided triangles, a rule that sends edges to subdivided edges, and a rule that sends vertices to vertices. And we also consider every possible injection between the left-hand sides and map them to injections in the right-hand sides. So this should do this computation. And some funny thing with this this rule system is that we can simply swap some arrows of the graphs to get another kind of computation of a Sierpinski graph. So I just give this as an example to understand how to read the rule systems. So here, as you can see, the triangle rule now applies only on acyclic triangles. And it's in its right-hand side, there is on two types of triangles. So on the outside, you have a acyclic triangle, and on the center, you have a cycle. So only the one on the outside will be further rewritten by the process. But in fact, so we want to check if this kind of local definition indeed gives this kind of functor. And in fact, we have a problem because colimits are not well behaved in the category GI. So if we take this kind of diagram specifying the gluing of two edges along some common vertice, or some glue vertice. So what I mean by that is that in the category of graphs, this should be the colimit. But if we go in the category GI, we have the property that we can observe that this cocoon is also a valid cocoon for this diagram, and there can be no non-injective morphism, no injective morphism from the green cocoon to the yellow cocoon. So the green cocoon is not the colimit here, and so one solution we can do is to still do the decomposition in GI, but do the reconstruction in G. So this is pretty easy to do. We just only modify a bit the global rewrite step. So we do the same thing for the first part. So first we decompose the input, we apply the local rules, which give us a diagram of local results. And then we follow the forgetful functor U from GI to G, forgetting that we have to consider only injective morphism in the computation of the colimits. So the global functor now, as the colimits are computed in G, the global functor becomes a functor from GI to G. And in fact, this caused a bit of a problem because I wanted to represent a dynamical system here, and this functor is not an undo functor, so it cannot be iterated. So the natural question here would be to check, is there a way to guarantee that this global functor preserves injective morphisms? But before answering that question, I will focus on the sequential computation of global transformation. And I will answer this question in a few slides. So what I mean by that is that if you have a global transformation, you can intuitively see that you can sequentialize it by finding an occurrence of some rule in the input object and find its local result and iterate this process while gluing local result together until you get the output. So in fact, this can be formalized by a general online algorithm to compute global transformations. And we can ask now, what does it mean to preserve the injection at this algorithm, at this sequential level? So what I mean by that is that through the whole process, we only add vertices and edges and never merge two existing ones. And what I've done is to define some local criterion on the rules that guarantees that this procedure preserves injection. And it also guarantees that the global functor over 90 that we have seen a few slides ago is those preserved injection. So to understand this, we must sketch a bit how the algorithm works. But so what we do is to compute a sequence of gluings, where a gluing is a colimit of some special class of diagram. So I call it a suture diagram, but in fact, it's like multiple push-outs at the same time. So this kind of diagram has two apex. So you have a partial result on the left and a new local result that you found on the right. And on the bottom, you have an arbitrary number of common sub-results. So this should compute this kind of new partial results here. And what we want to do is to guarantee that the green arrow from pi to pi plus 1 is injected. And to guarantee that, we can observe that the only way for this green arrow to be non-injective would be that the new local result Ri plus 1 impose merges of elements of pi. And in the sense, it should happen only if it asks to merge elements of its subresults. So if we forbid this a rule to merge elements of its subresult, we should get an injection preserving transformation. So this is the goal of this criterion. So I simply say that a rule system is incremental if for every rule, if for any rule gamma having two subrules gamma 1 and gamma 2, I forbid this rule to merge elements of gamma 1 and gamma 2. And I express this by saying that if R of gamma 1 merged some element of if in the R of gamma right hand side of gamma 1 we have merged some element of the right hand side of gamma 1 and gamma 2. Okay, I start again. If in the right hand side of gamma we merge some element of gamma 1 and R of gamma 2, then it must have been already specified by a subrule gamma prime of gamma 1 and gamma 2. And what I mean by element here is just a vertex or an edge. So merges can be only specified by subrules and not by bigger rules. So, and well, what I've shown is that if a rule system is incremental, then any morphism in the algorithm are injective, and also the global transition functor factorized through the forgetful functor u from gi to g. This gives us a functor from gi to gi that can be iterated as a dynamical system. Okay, so what we have done here is to guarantee some property of the global functor only by the mean of a simple criterion over the rules. And to go more in this direction, we can try to study the connection between the global functors and the local rules. And in fact, it is related to the notion of Kahn extension in category theory. So here I will recall what is a Kahn extension. So first, let's observe that the way that we computed our global functor T was to take a colimit for each of its input. So in the sense, each result of our functor is chosen as a base candidate Cocoon. And to compare this Cocoon, we used morphism between the apex. So as each output of the functor is the best candidate of in some sense, so the functor itself should be a best candidate functor in some sense. And to compare such functor, we will use collection of morphism from the output of a functor to the output of another that are in fact morphism between functor called natural transformations. And in this framework, we can express that T is the best candidate extension by saying that it is the left-hand extension of R along L in the two categories of categories. So what does it mean is that you take this diagram where you have the rules here and the global functor, and you first express that T is an extension of the rules by saying that there is a natural transformation eta from R to T after L, saying that if you apply T to a left-hand side of a rule, you get at least the corresponding right-hand side. And this property, in fact, could propagate to other objects because T is functorial. Then you take any other possible extension, and you express that there must be a unique natural transformation from T to K, making everything commute in this diagram. So as for colimit, this in fact characterizes our global functor uniquely up to isomorphism. So then global transformation is such a Left-Kan extension that can be computed with the colimit formula that we have seen before. And in the usual term for this is to say that it is a pointwise Left-Kan extension. Okay, so for as an example, I've studied the relationship between the global transition function of a cellular automaton and its local rules in terms of Kan extensions. So I will just sketch this a bit here. So we can see, so a cellular automaton is a function acting over decorated grid of cells that can be specified locally by a function only over finite sets of cells. And so the idea is to express the connection between these two functions in terms of Left-Kan extension. And to do this, we will first observe that there is intermediate configuration between the local configuration and the global configurations. So these are partial configurations. And this form, in fact, a whole poset of configuration in which the local configuration are included. So here we have only posets and a trivially monotonous function, but we can see them as degenerate case of categories and functors. So here I will be our left-hand side functor and the rows will be our right-hand side functor. Then we can define a global transition function phi from the poset of configuration to itself, just applying the rules whenever they can be applied in a partial configuration. So for instance, here we have 3-cell neighborhood, and by the rules, it should give us the white cell here. And on the right, we have another 3-cell neighborhood, which give us the black cell here. So in fact, we can prove that this, so first this functor, this monotonous function, in fact, encompasses the global transition function delta of the cellular automaton. And we can show that this is a Left-Kan extension in the two categories of posets where natural transformation are just witnesses of some monotonous function being smaller than another. And I've also studied what happens if you do the thing in the other direction by reversing the natural transformation here, which gives us the notion of a right-Kan extension and permits to express how we can localize some global transition function to a set of local rules. And last thing I studied on this is to try to lift this poset of configuration to be a category of configuration using shift isomorphism, which permits to represent some variation of cellular automatons where the space is shift equivalent. Okay. So now I will move to the last section, which is about non-determinism. So it's a big section. So my goal was to describe non-deterministic computation within global transformation. But I do not want to do an extension of the formalism, but rather show that it was already possible to be expressed in the global transformation framework. So this is in fact in complete analogy with discrete dynamical system, which are just functions acting over some set of states, where non-determinism can be represented by simply taking this set of states to be the power set of another set of underlying real states. In this setting, the function of the dynamical system is send set of states to set of states representing non-determinism. Okay, so as example, let's focus on the simplest of such non-deterministic systems, which are non-deterministic Lindenmayer systems. So these are simply function from global function from sets of words to from words to sets of words, specified locally by a function from letters to set of words. So the global function only does the concatenation of sets of words. As for instance, if we send the letter A to A or AA, and we apply this to the word with 2 A's, we get either 2 A's, 3 A's, or 4 A's. And one thing we can observe here is that the word with 3 A's is obtained in 2 ways from the input, either we duplicate the first one of the first A or the second one. And this information is lost by taking sets of words here. And in fact, this will cause an issue if we try to do the same thing with a discrete dynamical system by considering a category PW of sets of words and of sets of morphisms between words. So indeed, in this setting, the concatenation will not be the colimit of such kind of diagram. So here we take a diagram where we have two sets of words, and we have the empty word that is included at the end of each word on the left and at the beginning of each word on the right. So we can see this in terms of constraints as a set of concatenation diagram of the deterministic case. But what we want is that this set should be the colimit of this kind of diagram, where the morphism here represent the different ways of obtaining the words from the words in the diagram. So for instance, for AAA, it expresses that we can either take A on the left and AA on the right, or AA on the left and A on the right. But the problem here is that we can you can take this kind of cocoon, selecting only one way of constructing AAA. If, for instance, you can take only A on the left and AA on the right. And this makes impossible to find morphism M from the green set to the yellow set, making everything colimits in this diagram, showing that this concatenation is not the colimit in the category PW. So by trying a lot, we can conjecture that there is no category having for object sets of words and an appropriate choice of morphism begin and end, such that this kind of diagram gives the concatenation as a colimit. And whether or not this is true, we can add a bit more structure by recalling within the object the multiple ways of obtaining AA. So let's design a category OW of indexed families of words. So objects are indexed families of words, and morphism will be constrained to only pick a unique source word for each target word. For instance, here we have two families of words and a morphism F from the bottom family to the top family. And we say, let's say for BA that we have to select a unique source word. So here we take B, and then we associate the morphism 0 from B to BA. And with this added structure and constraints, we can finally show that concatenation can be obtained as a colimit of similar diagram, but with families of words. So here we have the empty word that is included at the end of each family, each word in the family on the left and at the beginning of each word on the family on the right. And this gives us the family of pairwise concatenation of the words in the two families. So here this operation, in fact, we call the different ways of computing AA. Okay, so now in this setting, in this category, we can from this category we can define a functor D from words to sets of to families of words corresponding to the global transition functor of some non-deterministic Lindenmayer system. So for instance, for the example that we have seen before, we send letters to the families of every possible local result for its letter. So here, D of A is a family containing A and AA. And for compound words, we take as indices tuples of local result for each letter, and the corresponding elements are just the concatenation of the words in the tuples. So what we can observe here is that in this setting, D of AA is the concatenation of D of A with itself, in the sense of the concatenations of families of words. So in this sense, D commutes with the concatenation, which permits to express to show that D is indeed a pointwise Lescan extension of its restriction only over the letters and the empty word along the natural inclusion from this restricted category to the general category of words. So if we restrict this functor to only acts over the empty word and the letters, we have enough information to recover it as a point for left-hand extension. And here we have nearly a global transformation. The only thing that that causes a problem here is that D is not a non-order functor going from as it goes from W to OW. If we try to fix this, we can try to lift its domain to be OW by following a singleton functor sending W to OW. But if we do this, we won't get a pointwise left-hand extension. So the only other possibility here is to make D composable with itself. And more generally, we need to answer the question about how to compose a functor F from C to OD with a functor G from D to OE. Okay, and this seems a lot like something that is well known for power sets. So I will just recall this. So we can compose a function F from R to PS with a function G from S to PT by first lifting G to be a function from to be a function PG from PS to PPT. Then we can compose these two functions and then flatten the sets of words, flatten the last set by taking unions of sets of words. So all of this define, so the lifting of morphism to morphism between two function, the lifting of function to function between power sets, in fact, define a functor P acting over the category of sets, and the flattening, the fact that we can take the flattening, this kind of flattening here, and that we have also a singleton function from a set with power set, is summarized by the fact that P is a monad over the two category of sets, the category of sets. Okay, and when we have a monad, we have a Clay-Lee category associated to this monad that describe this kind of concatenation compositions. So the object of the Clay-Lee category associated to P is are just the object of the base category. So here objects are sets, and morphism here will be represented by a little circle over the arrow and a tilde over the name of the morphism. So a morphism F from R to S in KP corresponds to a function from R to PS, and the composite of two such morphisms is just given by this kind of composition. Okay, so let's try to do the same thing, but for global transformations. So as we have seen in the part about CAN extension, the global transformation framework is a two-categorical framework. So we need to define two functor acting over the two category of categories. So this functor will send categories to their categories of families, functors between categories to functors between their categories of the corresponding categories of families, and also acts over natural transformations. But we can observe the same kind of structure as before. So we have a singleton functor from any category to this category of family, and a flattening functor from the category OOC to OC for any C. And so then we can show that this forms a weak to monad over the two categories of categories, which permits us to work in KO the Clay-Lee two category associated to this weak to monad. So this permits to state the following theorem. So so the idea is that if you take a rule system that represents a non-deterministic computation, because the left-hand side are taken in C and the right-hand side are taken in OC, we can construct a corresponding rule system here on the right here in the category of Clay-Lee. And we have the property that if we have there is a global functor T that is the left-hand extension of R along L in the two categories of categories, then this is equivalent to say that there is the corresponding functor T tilde is the left-hand extension of the corresponding right-hand side functor to the corresponding left-hand side functor in the category of Clay-Lee. So we do not have a global transformation in the usual sense, but we are equivalent to a global transformation in the two categories of Clay-Lee. And this is very, very easy to show. We just need to unfold the definition of the morphisms and the composition in the category of Klesley and use the fact that we have a weak to monad. Then this diagram will weakly reduces to this diagram. Okay, so for instance, for Lindenmayer system, we have already the left-hand side of this equivalence, and this gives us a way to represent non-deterministic Lindenmayer systems as global transformations. So, so we are near the end here, but before my conclusion, I will mention some subject that interested me recently. So, so when you do computations, non-deterministic computation over spatialized data, you can get spatial correlations. So spatial correlations are just dependencies between arbitrary distant local results. So for instance, if you take the same Lindenmayer system as before, but you add a rule that says that two adjacent A's must either stay the same or both duplicate, both stay the same or both duplicate, then if you apply this system over an arbitrary long sequence of A's, you get that if the first A duplicate, then the last A also have to be duplicated. So non-deterministic choices cannot be done at the local rule level. We need to wait, we need to do the non-deterministic choice at the global filter level. And if we do not want that, we can try to characterize correlation-free systems. So I've done this by a similar criterion than the criterion that we have seen in the for preserving injection. So the idea, the intuitive idea is that we want to guarantee that two distant local results to be independent. So we need to say that rules are independent and the dependencies between rules are common subrules. So what we need to say is that for any rule in my rule system, I will guarantee that any combination of results, if it's subrules, are compatible. So to express this, I say that for each rule, I will for each rule and for each combination of sub-results in its subrules, there must exist a corresponding result in the rule. And so this criterion, I've shown that this criterion works only when the category is co-complete. And the part, so there is ideas for making this work for categories that are not co-complete, but this involves shift theory, and this there is still a lot of work to do. So now I will summarize a bit what we have seen. So global transformation were presented as a general framework for describing synchronous computations. And we have seen that we can relate, in this system, we can relate the local level and the global level using CAN extension, which permits us to, this kind of tools permit us to guarantee some global properties of our systems by the means of the local rules. And also this formal framework is very general because it doesn't ask a lot of structure over our categories. And even the two categorical framework, the two categorical setting is a parameter here. One thing I didn't mention also is that not a lot is that there is practical implementations of the general online algorithm. So it has been tested over a wide range of structures like graphs, trees, and non-deterministic computations. As perspectives, so there is still a lot of work to do. For instance, for the question of guaranteeing global features through local criterions, I was only able to do this for simple categories such as the category of graphs because as it is a category of Preshev, it is complete and we can reason by considering elements. If we want to consider more constrained categories, but that can be still, but we still want to see them as gluing of simple blocks. We should extend the formalism to consider sites or toposes And I'm also trying to investigate if we can use adhesive categories or model categories of some theory. Other possible further work would be to study the complexity of the algorithm, but it is a very general one, and try to extend it by using the fact that we can reason about elements of the categories that we want to focus over which we focus. And as a more practical perspective, we can try to use this formalism to model real-life systems, but to do this, it will be really useful to extend global transformation to stochastic or quantum computations. So this is, I think this is all for me now. So I will be pleased to answer your questions. And thank you for your attention.
Thank you very much, Alexandre. Thanks for the very interesting talk. I apologize, I forgot at the beginning to invite the audience to ask questions writing on the chat, but now it's too late. Anyway, the usual way of proceeding with this kind of seminar is that we remain online till the end of this hour, till 4 o'clock in the question and answer session, and then possibly we continue on more offline for more specialized discussion if there is interest. This said, I invite everybody to ask questions or to propose remarks about the presentation. Is there any? Nicholas?
So maybe I just start. So thanks a lot, Alexandre. It was very interesting. And could you go back to this? I mean, yet at some point you had this the original version of the left-hand extension construction in some graphical setting. No, there was some example.
This one or?
Yeah.
Or
before you had like a
Cellular
concrete
Automata?
example where you showed how to express the Lindenmayer system in this language. No.
You want the concrete example? Or
Yeah. Just a concrete example.
This one?
No, the one for graphs. You had one for graphs where you showed that you can do the Lindenmayer system, I think.
The one
am I
which is
mistaken?
pointwise. The pointwise one.
Exactly.
Okay. This
one.
Yeah,
it was somewhere.
It is this one or?
Maybe.
Or not?
Okay. So I was just trying to understand. I think it was even a slide before where you show how this rule has to look like. You had like a slide where you have these inclusions until it flew by a moment ago. That one, just this one.
That
yes.
one. Okay.
Okay. So if I wanted to design myself a rule in your semantics, in this global transformation semantics, so do I have degree of freedom? I mean, you said something along the lines like here, for example, in order to get exactly that transformation, I have to choose. I mean, I somehow choose myself some graphs, which have some sub-object relationships. And do I have to have the entire lattice, or is it enough to just, I pick some sub-object relationships? So it looks like on the left-hand side, there seems to be like the lattice of sub-object inclusion, but not having, for example, just the two vertices.
Okay.
You see what I mean?
So at start, so here I say that I take only two functors, L and R, and I don't say any particular property about them. But at start in the formalism, we constrained L to be fully faithful. So what does it say is that for each object on the left-hand side, you have to consider each pair of objects in the left-hand side, you have to consider every possible morphism between them. But in fact, I think this property is not needed. In fact, so for some in some cases, such as in some systems such as cellular automata or context-sensitive Lindenmayer system, you want to express sometimes rules that have a pointed part and a context. And in these settings, this can be expressed by considering a non-injective left-hand side functor. But even if you have a non-injective left-hand side functor, you can always modify your rule system to get a fully faithful one. So
for example, it seems like you have, for example, I cannot have, I mean, I'm just trying to understand a little bit what is the semantics here, because by just giving the shape of functor, for example, I could have a rule which for, how you call it, L of gamma, I could have a lattice where, for example, you have this exactly this part you have, plus another part of the lattice where I have a, let's say, a square of edges in the same left-hand side graph. So I have two alternative. So are you saying something along the lines you need to have a complete lattice with sub, because I mean with supremum, because I mean if I could have two alternative things sitting there, no, a triangle which is not embeddable into a square. So you seem to be saying something. Okay. I mean, maybe then it's not the Lindenmayer system. I'm just trying to understand: am I free to choose any functor of that signature, or is there some underlying assumptions that I have to satisfy?
The question is that does it extend or not? But if you so here you talk about adding a square, okay,
and then maybe all of the inclusions that I can have, let's say, from this edge, yeah. And now it seems, because that seems like a non-deterministic sort of choice now, no?
It depends what is the right-hand side.
Well, and let's say for the right-hand side, here? I take, so you said you have some sort of subdivision scheme. And here now, I mean, it seems there's something missing from, I mean, this definition seems to not fully reproduce what you said, because you want to, so presumably the trick here is that I can then not at the same time subdivide a triangle like that and a square. There might be a trick, but I don't see it at the moment.
So in particular, if you suppose L to be fully faithful, you have to consider also automorphism of rules, symmetries of rules, and you have to preserve symmetries. And in this setting, I think it constrains a lot what should be your right-hand side. And so, but indeed, if you have a non-deterministic choice to do in the reconstruction, what will happen is that you will have multiple possible cocoons that cannot be compared. If it happens, there won't be a colimit in the usual sense. But what I mentioned for the case of non-deterministic correlation at the end is that I've observed that in the category the OC from some category C, we can take you can take colimits that corresponds to sets of cocoons of the usual the deterministic case.
And right, because now my second question was exactly. So my second question was now, because I mean I'm trying to understand. You seem to have a very interesting link between these. I mean, it seems to have, you can have systems which have non-deterministic choices. I might take some input graph, and sometimes I subdivide a triangle, sometimes I make a square or whatnot, and that seems to be expressible. I mean, did you already experiment with these non-deterministic choices for like these graph-like global transformation, or is that an outlook? I mean, you seem to have the construction in general, but did you parse that out for particular examples? I mean, does it give you interesting rhetorics?
The last thing I've seen, I didn't work on correlations recently, but I've seen this kind of situation where you have multiple possible results and you still get one colimit summarizing all these results as a counterexample of some of my propositions. So it was only in the technical sense. So I only designed for very degenerate categories having like 3 or 5 objects and some morphisms. So, but I think this is a really interesting direction. I'm really interested in this part. But
because somehow the other natural question would be sorry, and then I let the others sorry, just one quick thought was that somehow I can glue together certain of such lattices from smaller parts, and it seems to be an interesting question now that you have such an abstract view. Can you understand decomposing a global transformation? I mean, the specification of it, gluing it together from smaller bits so that you can have like an operational language for these global transformations. Okay, no, but I let the others ask questions. Maybe come back in the offline session.
Yes.
Thanks.
Romain, raise a hand, please.
Yes, I had a question which is a bit related to what Nicholas just said. Because if you want to be able to, for instance, consider a triangle and then a square and then whatever size of polygon for mesh refinement, maybe if you work at the level of cellular complexes, then you just have the fact that you have vertex, then edges, and then face is not necessarily fully specified, and you could try and define like subdivision of a face regardless of whatever is actually the face.
Could you repeat the last part, I think?
Because there, when you modify graphs, you have an edge, and then your triangle is made of 3 edges, and if you would have a square, you would have 4 edges and so on. But you might be able to reason at the level that you have a polygon, which is regardless of the number of actual edges, just saying that it's a face, and then which is an object of dimension 2, and then you have edges which are objects of dimension 1, and then vertices.
Yes.
And then you define, you try and define a refinement of a face regardless of what the face is actually.
Okay. So whatever the polygon is, it.
Yes.
So I didn't think about that, but in fact, I worked a bit on these categories to represent cellular complexes. But so we tried to do this kind of rewriting system considering faces so it works. Obviously, it works for simpliciter sets, but there is no such polygons in simpliciter sets. And for so we consider generalized maps or abstract cellular complexes, but I think I think so. I never seen this I never had the idea in these terms, but if you want to reason about arbitrary big polygons, there was a time I wanted to develop some way to describe families of rules. So we need a language to express rules for each polygons. But maybe if you know some structure that permits to represent the subdivision of some easily, yes.
Yes, because you were talking about generalized maps a few moments ago, and I believe that in this kind of representation, it's actually quite easy to abstract over some of the topology. But I was wondering if you should actually look for abstract cellular complexes, if you would be able to get anything. But it doesn't.
The original paper was about abstract cellular complexes, and I never went back to them. But indeed, you are right for generalized maps, because you can represent a face by a cycle. The notion of face is not explicit in generalized map, but the issue is that for the pattern matching, for applying a rule to, for example, a polygon of length 5, we need an explicit left-hand side representing this cycle. So this doesn't solve the part where we apply the rules, of where we find the site of application of the rules.
Yes, this I agree with. I was just wondering if you actually had a look about the abstract cellular complexes part, but you just said that you didn't want back to it. So I guess this answers my question.
But there is, this is a jungle for this kind of structure. There is a jungle of different versions. It's difficult to find the right one.
Yes, thanks a lot for your answer.
Thank you.
Okay, if there isn't any question at the moment, I have one, Alexander. I was interested to your notion, the notion that you mentioned of incrementality, which is, I don't know, maybe immediately afterwards, incremental computation. Yes, here my question is, in essence, you say that the global synchronous transformation can be performed one piece at a time. Okay, but you don't introduce. So the question, maybe the question is, if you also introduce to formalize these sequences of local transformations and situations and the results about equivalence of sequences of local transformation with single parallel transformation, because this is what would be natural from the perspective of graph transformation, where you typically apply local rules.
So
Did you consider these, or this was just let's say an analysis of the global step of transformation in order to guarantee that you have a unique result independently of the way you see the application of the local rules independently of the order, basically, of the reduction of the local rules.
Okay, so I didn't introduce the notion of sequence of local rewrites in the usual, I think not in the usual sense of graph rewriting. What I use is the notion of partial application of global transformations. So what you do is you take, so you see here you decompose the input, the whole input with the local rules. And what I've done is to define the notion of a partial decomposition and consider an increasing partial decomposition. So, and then at the end, so I only consider finite graphs, and at the end I can just prove that whatever path I choose, I always get the colimit, the general colimit. But I didn't have to express things like how do you say, like confluence or Church-Chaucer property, like in graph classical graph rewriting, because the computation is strongly normalizing. I don't know how to express this, but
well, the point is that you consider probably you start from a smaller part of the starting state, then you consider larger parts, which are one included in the other, and therefore clearly in the end you have the effect of applying the rules to the entire initial state, something like this. So it's not really,
you just need
you don't rewrite local independent parts, but you have you enlarge basically the matchup. Okay, yes, this is something different. I wanted to mention that in the old, well, there is an approach to distributed graph transformation classically in the double push-out approach, and this idea of rewriting a network of graphs where the overlapping of this graph is modeled by spans between them, basically.
By what dividing them?
You consider the state as made of various graphs, which can be of which you model the overlapping by identifying common subgraphs. Therefore, a span embedding the subgraph into two components, and then you have the possibility, according to the usual DP approaches, to specify rules for the subgraphs and for the various component graphs, and in this way you model the rewriting of the entire system, of the entire distributed system. And there was also some proposal in some very old paper about the DPO by Hartmut, where he had this star, so sort of situation where you don't have just a span, so a subgraph mapped to two graphs and on which you rewrite, but you had a star, so several graphs, and for each pair of them you had the intersection basically modeled as another graph. So just to mention that, okay, this idea of, but as you mentioned it also at the beginning, the idea of maximum parallelism in graph writing was also studied and certainly related to this. In your situation, no, okay, this was another comment, but
no, but I would be really interested to have the references, but for this paper, because I looked a lot in the literature, but I didn't find them, and it seems to be exactly what I need to do the state of the art of the connection between my formalism and graph transformation.
Okay, I will try to find the correct reference. I will send you an email. Okay.
If it's possible. Thank you a lot. But do you have a question, in fact?
No, the another observation is that at a certain point you were requiring that that if you have something which is the application of the rule merges something, then this has to be specified already by the rule, something like this. This looks very much like the standard property we assume by assuming adhesivity in the underlying category, that push outs along monos are monos, basically. Push outs preserve monos. Okay, so this is probably a place where you're. This is something I wanted to ask you, but you mentioned in the last slide the idea of generalizing the approach to arbitrary toposes or adhesive categories is fits perfectly with this idea.
Yes, but I find the two approach very different, so it is a bit difficult to make the connection, but I'm indeed working on it to try to embed one system on another. But for the moment, I need to consider a very complicated construction, so I am not sure how to do it. But thanks for the information about all of these attempts of describing distributed graph rewriting, graph grammars.
Okay. Push out stars, Romain already put a link. Let's quicker. Yes, in fact, it was the very seminal paper by Hartmut. Push out stars, I remember. If I can, I will continue with the last observation about the non-deterministic aspect, because it, in a sense, the claim that you can reduce non-determinism to a specific kind of determinism is, at the first sight, looks a bit strong, is perfectly motivated and perfectly correct what you say. The different setting probably explains the fact that this kind of non-determinism doesn't match with the kind of non-determinism we consider in graph transformation. And the basic point is that in your approach is to consider the power set monad, essentially. So the idea that you compute at each step all the possible results, all the possible non-deterministic results. The intuition that in graph transformation we have about non-determinism is the one that we inherit from Petri nets. So the fact that when we have two transitions which are enabled at the same time, we can choose one or the other. Okay, so the main focus about non-determinism is not in the traditional theory of graph transformation, is not about let's say the language oriented, about computing all the possible results, but rather in analyzing an individual run, which can be so individual runs which are in conflict because at a certain point you take incompatible choices. And then these non-deterministic runs can also be put together in a single structure, where typically you are not interested only in the results, but also in the points where you had conflicts. And this gives us the structure of processes, of non-deterministic processes, which basically we borrowed from the theory of Petri nets, and we generalized to the theory of graph transformation. So this is just a hint to relate the two words and why they developed in different directions.
So you say you can have conflicts and then fix them in some sense?
No, not fix them, but you collect all the results, but not only the final state of the non-deterministic computations, also the computations themselves, with a suitable representation, in such a way that you can look at the history and seeing where the conflict arose, and where the different branches in a decision point were taken. The structures which were we explored for some time ago.
But if I may comment on that, so it seemed like you were mentioning at some point in your construction that the power set monad was actually not the construction itself. Sorry, the power sets themselves were not the construction. You're essentially tagging the power set in a way which looks a little bit more like a multi-set construction in the end, where you have a certain. I mean, it seems that you are tracking also alternative ways to reach the same replacement sequence or the same state in that case, I suppose. So it's more like it's actually quite interesting, because that is more like combinatorists would do it. I mean, if you were to imagine you have a system which evolves over a structure that you want to count, you might wish to count actually exactly how many times you can get. In your case, in this Lindenmayer system, there was like how many ways could you get an a word or whatnot. So that is actually maybe an application that you could consider about generating functions for such combinatorial structures you get by global writing. So,
so the indices in the index set where I have some, but it makes me think about the other definition of non-deterministic computation that I mentioned before the talk, using presheaves, not only presheaves, to represent the non-deterministic choice. So the idea was to define open functor. So it's a functor that takes an input and some random noise, something that is supposed to be coming from the outside, representing non-determinism. And if you do this, you will get that the noise itself must follow, in some sense, the structure of your rewriting. So it must express which choices you do at which step of computation. So it make all of this. So I'm not used to what Andrea mentioned, but I feel a bit confused, and I see a lot of things that seems a bit the same also. So I don't know what to. So I should read about this way of representing non-determinism.
Excellent. Thanks. So Andrea, should we maybe close the session and go on in private, so to speak? I mean, still on. I mean,
I see that it is pretty late. Thanks. So thank everybody. Now Nick will shut down the YouTube streaming of the
Yes.
session. And maybe Nicholas, before closing, you want to announce the next seminar?
Yes. So we have I mean, the next planned talk is in 1 month on logical approaches to graph databases by Elvira Pino and Fernando Orejas. We might have one talk scheduled in between, so if you're interested, please subscribe to our mailing list. And I would like to thank again also the speaker, Alexandre. That was very interesting. And for everybody who might still be on YouTube, you can still join us for, let's say, like the next quarter of an hour, 20 minutes. We might discuss a bit offline. We stay in the Zoom meeting. And yes, so thanks, Andrea, also for hosting. And thanks for everyone to be here.
Thank you.
And I will now cut the YouTube stream.